All right, now that we've been spending this entire chapter working with triangles, we started out with classifying triangles as isosceles, um, scaling, and equilateral, and we're going to now take a look at the properties of both isosceles and equilateral triangles. So first of all, just a reminder of what the definition of an isosceles triangle is. It is a triangle with at least two equal sides. So the key word here is the fact that it says at least two equal sides. This means that every equilateral triangle, which has three equal sides, is a isosceles triangle. Now, not every isosceles triangle, however, is an equilateral triangle. So an isosceles triangle has at least two equal sides, and those two equal sides we call are the legs. And between those two legs, we have what's called the vertex angle, which is going to be up here at the top. It's between the two congruent sides. Then the side that is not necessarily congruent to your two legs, we call that the base. And then you have your base angles, which are going to be to the left and to the right of the base. So there are the parts of an isosceles triangle, and the reason we talk about those is so we can talk about the isosceles triangle theorem. The theorem says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So what this is saying here is that if I have a triangle here of ABC, and I can see that AB is congruent to BC, then the angle opposite of those sides are going to be congruent. So the angle opposite of side AB is angle C, and the angle opposite of side BC is angle A. If these two sides are congruent, then the two opposite angles are going to be congruent as well. Now we can also look at the converse of this statement too. If two angles of a triangle are congruent, then the sides opposite of those angles are congruent. So here I'm given that angle A and angle C are congruent. And what this is going to mean is that the opposite side to those angles are going to be congruent as well. So that gives me that AB is congruent to BC. So how does this help us out? Well, when we've been trying to find angles, it's very helpful to know how to find the two missing angles if you're dealing with isosceles triangles. Plus, when you get out into the real world and you're starting to look around, if you look around your house or different things, architectural elements that you're looking at, a lot of times you're going to see isosceles triangles. And to know how you're doing this and working with those angles is really important. So here we have two triangles, and more specifically, we have two isosceles triangles. And the first isosceles triangle that I have here, I have a vertex angle of 120 degrees. Well, if I wanted to find out what the two base angles were, because it's an isosceles triangle, I know that my two base angles down here have to be congruent to each other. If the three angles add up to 180 degrees, that means that the two bottom angles here have to be the remainder of the 120. So by taking 180, subtracting 120 degrees, I am left with 60 degrees. Now 60 degrees needs to exist in both angles down here for my base angles. Because they are equal to each other, if I take 60 degrees and I divide it by 2, I end up with 30 degrees. So both of my base angles are both going to measure 30 degrees. Now this triangle here adds up to 180. If I transfer this information over into the second triangle, and that second triangle is also a isosceles triangle. Well, it's hard to do anything without getting any given angles, but I do have a vertical angle, which means that I can bring my 30 degrees over into the triangle here to the left. Now, if I have an isosceles triangle, my two base angles have to be the same, which are going to be the sides opposite of the congruent sides. So 30 is one base angle, and my other base angle is going to be here to the left. So now I have 60 degrees total, and I need to find out what my top vertex angle is. So if I take 80, subtract 30, and subtract another 30, we're going to be left with 120 degrees. And so my angle for the vertex angle is 120 degrees. Now, looking at these two triangles that we have here, they are clearly not the same size. However, they do have the exact same angles. Now, just because they have congruent angles does not mean that they are congruent triangles. This right here is actually looking at two similar triangles. They are proportional to each other, which means they can have all the same angles, but they, in this case here, are not congruent. If you had a equilateral triangle, where you would say that since we know the theorem for an isosceles triangle, that all of the angles opposite of the congruent sides are all going to be congruent to each other. What that's doing here is that's taking this triangle, which all three angles would add up to 180 degrees, and you're going to have three congruent angles, which ends up giving us 60 degrees. So each angle on an equilateral triangle is always going to be 60 degrees. And there we call this an equiangular triangle. So when we talk about an equilateral triangle, a triangle is equilateral if and only if, or sorry, it is, oh, I've got this twice, sorry. It is equilateral if and only if it is equiangular. And what that just means is a triangle is an equilateral triangle if and only if all three angles are the same, which in this case here, all three of those angles are going to have to measure up to 60 degrees. So now that we've taken a look at our properties of an isosceles triangle and equilateral triangle, I want to go through here and just talk about how we can use this information to set up a two-column proof, because this is everyone's favorite thing to do. So first of all, what I'm given here is I have that segment AB is equal to CB and CB equals BD. So I have these three segments here that are going to be congruent to each other, and I also have that angle 1 is congruent to angle 2. And what we're trying to do here is ultimately prove that angle A is congruent to angle D. Well, how we can do this is a couple different ways. And first of all, one way you can do this is by proving that the two triangles are congruent to each other. Well, the only problem is that if I set up the information that I have right now, I have side-side angle, which is the bad triangle because it makes up a bad word. So I cannot use my four postulates that I use for triangle congruence. So we're going to go about this a slightly different way. So with all the information that's given to us here, I have two isosceles triangles. There's one in yellow and there's one in green. Well, because of the isosceles triangle theorem, that says that the two base angles have to be congruent to each other. So in this yellow triangle, since CB and BD are equal, this means that angle 1 has to be congruent to angle D because of the isosceles. Because of the isosceles triangle theorem. Because you have two base angles that are congruent to each other. Same thing goes here on the green triangle. If it's an isosceles triangle, because CB and BA are congruent to each other, this would allow me to say that angle 2 is congruent to angle A, and once again because of the isosceles triangle theorem. Now with this information, since angle 1 equals angle D and angle 2 equals angle A, and I already know that angle 1 equals angle 2, we can substitute the fact that angle A is going to be congruent to angle D using substitution. And so there we've completed our two-column proof, which is using the isosceles triangle theorem. So now that we have talked about all of the properties that go along with triangles, there's many more that are going to come up later. but here you should have a general idea of definitely how to find all the angles that are associated with triangles, and then trying to, work with our triangle congruence as well. Like always, if you have any questions, make sure that you bring them up to me in class tomorrow.